Okay, so the final question that you have is you need to model a pericyclic reaction. And I know you've never heard the term, so we'll quickly cover what you need to know, the bare basics that will give you insights into the question. So pericyclic reaction is basically what it says. It's a cyclic reaction. So one of the types, the specific type we are going to look at is called a cyclization reaction. So in other words, you're forming a ring, making a ring from two non-ringed species. It might contain a ring, but you're making another ring. You're making a new ring in essence. And it's different from most organic reactions because most organic reactions are ionics. In other words, you have a minus, something minus attacks something positive, anions and cations and intermediates, etc. But pericyclic, basically, like I said, is electrons moving around in a circle. So if you look at these species, and it happens to be, you always need some sort of unsaturated bonding in your molecules that you consider. So there's a double bond, there are two double bonds here, and then electrons can move. So that those electrons move to there to form a sigma bond there. This forms a pi bond there. This forms another sigma bond there. In other words, you see we go from 3 pi bonds to 1 pi bond. We also introduce some stereochemistry. Interesting story. Peri and the prefix means around or about. So technically it's around cyclic reactions, interesting. It's always interesting to know where these words come from. But yeah, in essence, this is the mechanism. Just spend some time. I'm quite sure you can see them. It's just pushing arrows. You form the bonds. So how do these actually work? Now, any organic reaction, I hope you've deduced by now, we can use molecular orbitals to understand why they occur, why they are favored, where reaction sites are more active, which reaction sites are more active, etc. Where the least amount of electron density is, where the HOMO is, where the LUMO is, in other words, which sites are the bonding sites. That's basically what it is, and that's what organic reactions are. So in general, also, the pi molecular orbitals, in other words, the double bond orbitals, molecular orbitals, are where interesting things take place. If there's one of them, I mean, if there's none of them, then you have different kinds of reactions. But in general, if there's a double bond in some case, whether it be a carbonyl or alkene, that is where you should start looking for a reaction to take place. So if we look at the reaction mechanism, we just looked at this one. If we consider the p orbitals in the double bonds, remember the p orbitals make up our double bonds, in other words, the pi molecular orbitals, as we saw earlier. So here's a p orbital, there's a p orbital, there's a p orbital, p orbital, p orbital, p orbital. Okay, and that is what actually is taking place. There's some sort of reaction here. So we think there's a double bond there, so it means these two p orbitals need to interact. This p orbital needs to interact with that one, and that p orbital needs to interact with that one. So to help you out a bit, if you draw it in perspective, so there's our mechanism at the top. So you tilt this one so that it's over this one. So this one is on top of that one, right? And now we put in our p orbitals. We have, and we choose them, that we need to choose in terms of either this one's HOMO and this one's LUMO, or this one's HOMO and this one's LUMO. Okay. Argue for yourself why. So the one's LUMO is always going to bind to the other one's HOMO, or the other one's HOMO is always going to bind to the other one's LUMO. And because they're periodic, they will always give the same reaction bonding. They won't give different reactions necessarily. Sometimes they do. Okay, that's actually a lie. So ignore the first statement. So you need to see which one's HOMO and which one's LUMO. This one is actually doesn't matter which one it is. So in terms of what happens here is we have, you see these two are in phase, these are out of phase. So how would this pi orbital, or how does molecular orbital look like? It would look like 4 lone p orbitals basically. And this one is an in phase. You can see because the shaded region is on top and the empty region is at the bottom. Now, This means this allows for this bond to form there because, you know, shaded, 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 shaded. The green and the black are just for illustrative purposes where the bonds are going to form. So then what happens is you form a big blob here from that, you form a big blob there from that, and these two can positively overlap with one another, side-on overlap to form a pi bond. So what is this? This is sigma interaction. This is also sigma interaction. So that's then what happens. So you're going to calculate the molecular orbitals. You can argue it with using your HOMO-LUMO orbitals as well. So you can have all of them in phase, for example, all of them or in phase, out of phase, in phase or in phase, out of phase, depending on your HOMO-LUMO. You can use your calculations to guide you as to which ones are the HOMO and which one are the LUMOs. So look at both HOMO and LUMOs for both molecules. That's what I'm saying. Okay. And then you draw them in perspective, and then you see where the bond comes in. But now the stereochemistry is quite cool, because if you look at it from this way, so you can see here's the hexagonal ring, right? Hexagonal ring. So 1, 2, 3, 4, 5, 6. There's the hexagonal ring, there's that double bond there. And we look at it like that. The R1 group is coming out of the plane, the R2 group is going into the plane in the line of sight. And that's why we have the stereochemistry as such. And that's what I ask you to do later on as well. So go on, calculate these. So as I said, HOMO-LUMO. So you can choose. Either one's HOMO, either one's LUMO. See how they look. See if you can figure out what the p orbitals are that causes these interactions. How they look. And you can draw it schematically for me like this, and also show the computational route. So in other words, how does the molecular orbital look? Because remember, the computational aspect is not going to give you loose p orbitals that I did here. It's going to give you how does the molecular orbital look. It's going to be a bunch there, and then 2 p orbitals like that. This one is just going to be nicely grouped there at the bottom. Okay, I hope that was enough information. If you would like to read up more on pericyclic reactions or that kind of thing, just Google it. I promise there's a whole ton of work. It's actually one of the major fields in organic chemistry. You'll find enough information on it. Okay, good luck. Yeah, this is the final video, so good luck.